Now let us illustrate the application of simulation modeling to analysis of pandemic impacts on supply chain performance and supply chain resilience. We consider a supply chain network design of global nature, which comprises of upstream manufacturers in China, which are marked here with yellow icons, that ship their products to 3 distribution centers in South America, Europe, and in the United States. And from there, they are shipped to customers. Let us show this material flows more depictively. In the United States, there are also some regional distribution centers which are served from the center of the city in Houston, and from there, the goods are delivered to customers. Now we are following the real-life timeline of the COVID-19 pandemic and assume some scenarios of pandemic propagation to understand and predict the impact of such pandemic propagation in the world on our supply chain. First of all, let us take a look at the data that we use in the simulations. We have 5 different products in our supply chain, 95 customers across the globe. The supply chain consists of 2 factories, 3 major distribution centers, and 4 regional distribution centers in North America. The customers have periodic demand. For example, the customer in San Diego orders every 5 days 24 units. Here we assume deterministic demand and deterministic order intervals just to avoid any additional randomness for result interpretation. Of course, it is very easy to introduce variability in demand as a stochastic distribution, and also variability in order interval if we need to do that. We also have expected lead time associated with each customer. For example, lead time of 4 days means that our customer in San Diego places an order on Monday. We should deliver by Friday. Otherwise, if we deliver on Saturday or later, this order will be considered as a delayed order, which will negatively influence our on-time delivery, our service level performance statistics. We have some facility expenses associated with factories and distribution centers. First of all, fixed facility cost and inventory holding cost, which is variable. Our facilities operate at continuous review, inventory and production control policies with some reorder point and target inventory. Transportation passes in the network are associated with some costs, which can be product and distance based. For example, 20 cents for 1 unit of product and 1 kilometer, or they can also have some fixed rate, especially for long distance transportation, like for example from factory in Xiamen to the distribution center in Houston. We consider 3 periods of time, with whereas in one period we have different demand, which will be 50% of demand, following the logic of real-life pandemic, where demand dropped significantly in spring and summer 2020 for many products due to lockdown measures undertaken to control the pandemic propagation. We also have some processing costs, inbound and outbound shipment costs. Our production it's subject to some maximum design capacity. For example, if we say the factories are able to need 0.01 days to produce 1 unit of product furniture, it means that they can produce 100 furniture units per day. This maximum design capacity. The real capacity is determined by inventory control policy, min and max values at factories. We also associate some production costs for manufacturing of each unit. In shipment, we define material flows, sources and destinations in this multi-echelon supply chain and the associated vehicle types and rules for minimum possible loading in our transportation network. Then we have sourcing, which based on the fixed source, single sourcing policy, and parameters, capacity parameters associated with transportation means. Well, now let us define a scenario for analysis in terms of events. We follow the real-life timeline of coronavirus pandemic dynamics. Our first event will be closure of factories in China on the 25th of January 2020. Exactly, this corresponds to real-life dynamics of COVID-19 pandemic. For this particular scenario, we can assume that, yes, and we define this disruption as event temporarily closed for factories. In 45 days, on the March 10th, some factories in China reopened, and we define it as an associated event, reopen factories. This event is associated with the event number 1, closing. In 45 days after closing, they reopen. However, the pandemic has not been localized in China. It propagated across the globe. As such, we should define events for distribution center closure and opening following the pandemic control measures undertaken in Europe, United States, and South America. Here we consider a time lag of 60 days after the beginning of shutdown measures in China. In 60 days, so on the March 25th, the distribution centers in Europe, North America, and South America close. And they reopen, let us say, in 90 days. Wow. So now we can run our simulation experiment. The simulation allows us to analyze impact of the pandemic propagation on supply chain performance for different and interesting performance indicators. For example, we can analyze impact on production, impact on profit, cost, so financial impact, impact on the customer performance measured by on-time delivery or service level, impact on our lead time, inventory management, if we would have any backlog and what is our inventory dynamics, and impact on demand fulfillment. Let us run the experiment. So we can see that at the beginning of the year, everything runs smoothly. We have material flows. We are now in January. Yes? So, and remember that on the 25th of January, the Chinese factories, zoom a bit in this direction, the Chinese factories will be closed. Right, so the factories are not producing anymore. There are some goods in transit, but there are no new deliveries. We can see that this has negative effect on service level, right? Because not too much inventory was available in warehouses, and the service level has negative effect. We also see that lead time increases significantly for many orders. We are late, right, due to the missing supply from China. Now the supply in China reopens on the 15th, right? It starts producing. However, unfortunately, on the 25th of March, the distribution centers in North America, South America, and Europe are closed, right? Central was closed. The problem here is that even if some materials are arriving from Chinese factories, they cannot be moved to the customers. And so we have backlog in our system for some products, and problems, obviously problems with fulfillment, right, which is quite low for some products. We see drops in our profits, right? So we are actually having losses here, and this is something which leads also, which it can be explained by huge backlogs. So we said that 90 days was the quarantine times in Europe and United States. So now everything is working again, the supply chain is recovered, all objects are working. We can see positive effect on service level, which starts increasing. If we switch from a cumulative view to daily view, we can see that now we are more or less better as through the time where everything was closed. However, we are not able to recover to 100%. Our average service level is still very low. So we can quantify the impact of pandemic propagation or some anticipated pandemic scenarios on our supply chain performance. Here we assumed very severe disruption, right? We assumed 90 days of quarantine measures and associated demand decrease of 50% for the time of quarantine and lockdown measures. If we investigate a more optimistic scenario, say demand would not fall, it would stay same as before pandemic, and if we would say now that the quarantine measures would be not 45 days, but maybe only 45 days in South America, in North America, and in Europe. So, so the situation can be different. Let us save these results of the very pessimistic scenario of a pandemic. And now we are running, we will run experiment for new data, for more optimistic scenario. So let us do it a little more faster. What we can see is that pandemic impact is still high. If we compare profits here, for example, we can see that our total profit in the optimistic scenario, it's 8.8, say billions, 8.8 billions or 8.8 millions. And in the pessimistic scenario, we had loss of minus 2.26, which means that if optimistic scenario of pandemic would happen, the performance impact would be not so severe and negative as in the case of pessimistic scenario. And so one can use such simulations model, to very quickly define different scenarios, so events, and see which impact of pandemics can be observed in supply chains. One can change, for example, begin of shutdown measures, investigate the impact of duration in the upstream part, investigate the impact of changes in speed of disruption propagation if, for example, lockdown measures in Europe would begin not in 60 days after the Chinese measures, but maybe 90 days or 30 days. It will definitely have different impact on supply chain performance, because through these simulations experiments we have observed the timing of facility opening and closure in different parts of the world and different echelons of supply chains. This has the most crucial impact on supply chain performance. If there are some overlapping time windows when nothing works, or when opening and closures are not synchronized, all this can lead to very severe impacts on performance. In other cases, as we have seen in the second scenario, the impact was lower. Right? One can also change duration of lockdown quarantine measures downstream, as we did in the second scenario, and see its effect. So I hope with this example you could understand the value of simulation modeling for analysis of supply chain resilience and performance and disruptions and such severe disruptions as pandemic, and insights, managerial insights, which can be obtained through such simulations.